Hello, dear attendees. My name is Alexander Anisimov, and I work in the Sberbank team doing a recommendation system. Today, I'm going to share with you our experience how to improve recommendation system based on different data sources, or several data sources. Let me start with explaining how a regular single domain recommender system works. For instance, we have data that's available to users that use certain products. They can they can write their reviews. This is an example. Quite often you add attributes to this that describe the users or the products, and sometimes even the context in which the interaction happened. For instance, the time when a squirrel ate the carrot. So our goal is to learn to recommend foodstuff to the squirrel. In real-life systems, it's not only about a single source of data. Part of the information may be hidden in another domain. For instance, instead of food preferences, we can use drink references. That will let us learn more about the user interest and improve our recommendation. But in this case, let me note that the goal has remained the same, to recommend the food. So we'll call the main domain target domain, and the one that we're going to take additional information, just a source. What are pros and cons using the source domain? Let's start with pros. We learn more about users and about more users from the sources. That's why using them makes it easier to solve the cold start problem. In addition to that, it's usually accompanied by an increase in the diversity. But there are also drawbacks. The biggest one is that new data may bring not more than bias or noise. Quite often, it can be accompanied by a strong adding extra complexity to the inference pipeline, because we need to integrate the data processing steps and the learning process. Also, the current engine may not be fit to use an entire new source. And finally, the last hurdle could deal with the data privacy. Because Sber is still a bank, we can't share information about our clients. Can we resolve these cons? In order to offset or mitigate the confidentiality factor, we can use embedding that you'd get through encrypting the information about the source. It turns out that it's not so difficult to integrate the solution. We just generate a set of attributes for each user. And now, more and more often, recommender systems don't only use a matrix decomposition, but also other models with the ability to add these user attributes. However, this usual encryption can bring in noise, continue bringing noise. And because most methods focus on identifying patterns in the source domain, it may not happen that these patterns will be related to our target. For instance, we've used the dimension reduction method for user reviews about books, and as a result, we got vectors that characterize the geography of users, for instance. But it's obvious that geography will play a much less role in film recommendations than the genre preferences that we could derive from book preferences. That's why it's going to be much better to use additionally trained embeddings, tuned embeddings, that would mix information from both sources. This way, we have set ourselves the following goals: to learn to tune embeddings from third-party sources in order to use them in recommendations as parts of the target domain, and to study possible gains or losses that we may have. So let's move to the experiment. In terms of the progress, let's start with baseline models that were trained only using one source, the target domain. This domain contains user interactions with a certain multimedia system. The graphs here show how the prediction quality was evolving with each model, depending on the number of past interactions between the user and the service. We have 6 models here. There's established classic as matrix clustering. We have normal recommendation of the most popular items, but we also used neural networks such as autocoding. The leader here is item-to-item approach and autoencoder. We can also see that the results on cold users are almost the same everywhere. So, having looked at the baseline, let's ask a question: how to combine 2 sources in a single model? As a matter of principle, just like in classic recommender systems, there's a great deal of diversity of methods how to do that. But because our time is limited, we'll only focus on some of them, on those that we've tested, or better to say, on a certain subset of those that we've tested. Because the autoencoder turned out to be quite good, it made sense to extend its architecture and turn it into a domain encoder. In this case, we only added our own encoder for the domain source. And so the result is obtained from mixing outcomes from both encoders. You can use a popular idea from transfer learning that's called domain adaptation. In this case, we add a discriminator into the architecture that is trying to differentiate between encoder outputs. But at the same time, we have tools as part of our architecture that make these encoders to return similar vectors. And this is done through reversing the gradient in the process of reverse propagation of the error. In other words, we're just making the encoder of the domain, the source domain, to adapt the same characteristics that the other encoder uses for the target domain. Let's compare these 2 models with the best baseline models that we've had. Here on the graph, we've kept the 2 best models where only one source was used. That's our target domain. That's yellow and blue. Also, we've left the most popular model to just mark the lowest boundary. And we can see that adding the other source only reduced the performance. But for domain adaptation in red, we see positive effect compared to the baseline autoencoder. But of course, it makes sense. It would make sense to see an uplift for cold users, the leftmost points, because potentially these are the first ones who should have gained through adding the new data, because in the past we hadn't known anything about them, and now we know at least something. So this was the situation where we used raw data. But as we've already discussed earlier, they can contain noise. In order to reduce noise and make input data more useful, let's use the encoder parts of the proposed architectures. So we'll take our neural networks, remove the results from the layer in the middle, save it, and use the data as a separate user feature. As a result, we're going to get a graph that's shown in this slide, a curve in this slide. Almost the same thing, except for the purple line, which is now responsible for the domain adaptation neuron. But we added input information from the trained model, trained embedding embedded there. You can see that the result has grown even more compared to the previous leader among the neural networks, but we still have no improvement for cold users. In order to make sure that tuned embeddings offers any value, let's see how it's changed for raw data. The blue bar here is the metric for raw data, and the yellow one is for tuned ones. And we see that it helps us in 4 out of the 5 models. In conclusion, let's move to quite the bar charts that are quite busy, but I mean, you can get presentation later. Here, same colors represent the same domains. The blue ones identify the baseline models. On the left, we have performance for all users, and on the right, only cold users. As a baseline level, we've identified the autoencoder performance for comparison. What kind of conclusions can we arrive at based on these graphs? Well, firstly, tuning does work, but only if we are to use neural networks for that. Once we've taken out user embedding from the model, it didn't give us an uplift. Also, in most cases, the additional source allowed improving performance among the same class models, but not models have easily tuned to new sources, and so were perceiving it more like a noise. And lastly, for cold users, we only managed to improve the picture by using the combination of SVD composition and domain adaptation of the embeddings from domain adaptation. Let's now move to the last slide, conclusions that we can derive from this work. Repeating again, the tuning of source data helped us to reduce the noise from the domain, and the domain adaptation coder-decoder turned out to be quite a good tool for this. I would like to separately note that the encoder-decoder architectures suits well the RecSys task, and it makes sense to test them and try them out. The architecture is quite simple. It just takes to tune them, and basically the result turns out to be quite stable. I would like to separately mention that when using an additional transaction source, we weren't able to improve the cold data, even though one would believe that they would be the main beneficiaries. This activity is still at the active research phase. We are planning to use other sources to test them online for different recommender systems. And in the future, we will certainly share our results with you. With this, I've come to a close of my presentation, and I'll be happy to take questions.